section 13.11 is called Characteristics of Squirrel Cage Induction Motors. And what we're going to find out, a lot of times we're working with electrical machines, motors, generators, transformers. It's easier to look at characteristic curves, typical data sheet entries versus, trying to do the math, because, a lot of the curves that are associated with electrical machines are pretty complex. And so, what we typically do, when we get away from school and we forget all that math that we were taking, we look at curves, we look at tables, and we pull the information out from those that we need. All right, and so one table that I think, sort of gives an example of that, it's not exactly what I'm talking about, is this table that's found on page 276. And it's simply titled Typical Characteristics of Squirrel Cage Induction Motors. And we're going to go through that and look at it, and then be able to make some determinations with a real world application based on just these typical characteristics, instead of having to do some precision specific type calculation. So let me bring that up, and I think this will make, of course, more sense when we're looking at the table. So here's the table I was referencing. It's table 13A in your textbook on page 276. It's titled Typical Characteristics of Squirrel Cage Induction Motors. And as you can see, it's a pretty generalized look at this subject. As you see here, we're looking at motor size and defined as small and big. Okay, so that continues across the chart: small, big, small, big, small, big, small, big, so forth and so on. And then, in addition to that, what we're going to investigate, along with the relationship to motor size, is the per unit current, per unit torque, per unit slip, the efficiency, and the power factor. And so we're going to look at each one of those factors. Now, it's kind of interesting to note, and I'll point this out to you, and of course it's brought up in the discussion as well. But a small motor means anything under 15 horsepower. Now, 15 horsepower is a pretty good size electric motor. And then a big motor means anything over 1120 or 1500 horsepower, up to 25,000 horsepower. So what do you look at that and you go like, well, wait a minute. I have small, which means up to 15 horsepower. And then I have big, which is over 1500 horsepower. Okay, there's a big area there in between, right? That's not specifically referenced. And so, keep that in mind when we go through this, and, make sure that you understand as we explore, this particular topic. Okay, now let me get back dialed in on this thing. Flaked out on me. Hold on. Okay, and a couple other things I'll point out there. I already mentioned that current and torque are expressed in per unit values. And when we're talking the base current for a motor, we're talking about its full load current, and all other currents are compared to that. And then the other thing is the base torque is the full load torque, and all other torques are compared to that. And the base speed is the synchronous speed of the motor. And we've just gone into a lot of detail about that recently as well. So anyway, we're going to walk through some explanations here and look at the table and see how these relate to these particular motors. And I guess the first thing we're going to look at here, he tells us to look at a motor at no load. And when a motor runs at no load, it says that, so we're looking, let's draw this up here. So at no load, we're right here. And we're looking at the current, torque, slip, efficiency, and power factor at no load. And what we see is that at no load, the stator current is between 0.5 and 3 of the full load current, okay? So, you know, to put that into a different vocabulary, use a different term, you know, 50% of a 50% of the full load current the motor uses at no load. The larger motor uses, you know, less than that. So at the torque, of course, since there's no load connected to it, it's zero. There's nothing to look at there. And you know, in terms of the slip, it's close to zero. You know, it can't be exactly zero. And we you know, we kind of went through those reasons earlier when we were looking at those sections. The efficiency, of course, is zero because it's doing no useful work. And the power factor, you know, in relation to a no load, and so this is internal to the motor, right, is 0.2 for the small and 0.05 for the large. Now, something that we'll see, you know, throughout this is this idea that the larger the motor, the better the efficiency of that motor. And so, you know, we'll see that carry on throughout everything that we look at in this section and the sections to follow. Now, you know, a little more explanation. You know, he says the no load current is similar to the exciting current of the transformer. It's composed of magnetizing components that create the flux and a small active component that, you know, we account for the windage and friction losses in the rotor and the iron losses in the stator. So that whole section, you know, we went through and we quantified all these losses. You know, those of course were defined in terms of a DC machine, but here we're seeing them also related to AC machines. And the mutual flux links both the stator and the rotor. So, you know, all of those things you know, have their specific designation as we go through here. Now, he goes on to say too, and you know, we won't get to this point, but you know, sometimes, and we didn't do a transformer study before you got to this, but you know, as you relate a transformer, you can almost look at a motor, you know, in terms of a secondary and a primary between the stator and the rotor. You know, it's still that magnetic field that's the medium for the transfer or conversion of energy across there. But anyway, he says that considerable reactive power is needed to create the revolving field. And to keep it within acceptable limits, the air gap is as short as mechanical tolerances will permit. You know, a larger motor does typically have a larger gap between the stator and the rotor. Then he goes on to say the power factor at no load is really low, around 20% for small machines and about 0.05 for larger machines. And then I just mentioned, of course, that the efficiency is zero because the output power is zero. So now we shift to the next part of this, and that's when the motor's under load. And of course, that's going to be given to us here, right? And when the motor's under load, the current in the rotor produces a magnemotive force that tends to change the mutual flux, and this sets up an opposing current in the stator. The opposing MMFs of the rotor and stator are very similar to the operating magnemotive forces in the secondary and primary of a transformer. As a result, you have these leakage flux that, one is not necessarily coupled to the other. Not all the flux produced by the stator is coupled to the rotor. And, so there's those losses there. And the total reactive power, remember, it takes reactive power to create the flux. It takes reactive power to create the flux. So the motor's actually, it's greater than when the motor's operating at no load. However, the active power absorbed by the motor, is proportional to the mechanical load, and the power factor of the motor improves dramatically as the load increases. So let me put that in English. As the load increases, a higher percentage of the power becomes true power to produce this, power needed to run the load. When it gets to full load, you should see the maximum efficiency at that point. Is what he's trying to say there. At full load, the power factor ranges from 0.08 to 0.9 for large machines, and the efficiency at full load is particularly high. Okay, and look at this. And this is, in our power systems class, we look at these numbers, and at some point, if you've got a machine that is up to 98% efficient in converting, say, electrical to mechanical energy, like what you would find in an electric vehicle, then at some point that efficiency is going to win the day, because an internal combustion engine at its best is what, 20% efficient in converting gasoline into mechanical power. These efficiencies are going to win the day someday for electric vehicles, and I think we're fast moving to that happening. And if you're interested in that sort of thing, and you see yourself wanting to go learn more about that, our ELC 231 is a class where we explore those kind of topics. But anyway, the torque, of course, it's going to be 1, because it's, the per unit value is based on full load. And the slip for a small motor is what, about 3%. Here he says 0.03. And here for the big motor, it's much smaller. And again, the advantage in almost every case is to the large motor. Efficiencies improve upon the larger motors. The only thing that I would say there that does come into play with a larger motor, sometimes you run into bigger issues with heat dissipation, which changes things. So, that part of it. And then the last thing we'll look at is locked rotor, motor startup. And this is important, and we're going to move into a discussion about this in the next section. But locked rotor, or when the motor is, initially at startup, the small motor current is 5 times the full load current. And for big, it's 5 to 4, up to 6, okay, depending, on particular motors. The torque at locked rotor is 1.5 times the rated torque, up to 3, and 0.5 to 1 for the big motor. Okay, so there's some interesting comparisons. The slip, of course, is going to be 1, and we understand why that is, right? Because of this equation, and that becomes 0, and then that becomes 1. So there's that. The efficiency, at startup it's 0, because it's you haven't gotten to the point to where you're delivering power. And then the power factor at locked rotor is 0.4 and 0.1 at that point. Okay, so that's the way this chart reads. And then we're going to come back and actually use this chart in a calculation that follows in section 1312.